We've been talking about PageRank as a measure based on the idea of direct endorsement, a kind of single value for each page showing its quality, right? And pages of high PageRank should in turn have greater endorsing power when they go to link to other pages. And the question was, if we use this PageRank update rule, each page takes its PageRank, divides it up, hands it to the nodes it points to, then where will the PageRank end up as we keep applying these iterations? So there's a basic fact that turns out to be very useful and sort of brings some conceptual clarity to this whole notion that says that if I'm in a network that's strongly connected, then in fact there's a unique set of equilibrium PageRank values which don't change when I apply the basic PageRank update rule. So these are numbers that I can put on the nodes so that when I apply the rule, I get exactly the same numbers back. In the example we've been talking about, a strongly connected graph on 8 nodes, I've drawn the equilibrium numbers here. And you can check that they actually are in equilibrium, right? So I've got 6/20ths, or in other words 3/10ths, at the top. And if I were to divide that into 3 pieces, that would be 2/20ths to each of those outgoing nodes. And sure enough, B and C get 2/20ths as their PageRank, which is their current value. That's the sense in which it's in equilibrium. And similarly, you can check that C and E and F and G and H and A itself are also regenerating themselves under these numbers when I apply the update rule. And in fact, if this network is strongly connected, there's going to be a unique set of equilibrium PageRank values. We're not going to prove this fact, but it is useful to think about how you could find the equilibrium that we now know exists if you were handed a strongly connected graph. Right? I pulled these numbers sort of out of thin air. I wrote down 6/20ths and 2/20ths, and we checked, right? That's the great thing about this definition. You can check that it's an equilibrium. But how would you have found these numbers in the first place? Well, on a lot of graphs, you can actually run the iterations, and subject to some technical conditions, those iterations will actually converge to these equilibrium numbers. But we can also try to solve for them directly by solving essentially a sequence of equations. Right? This is effectively a computation that Google is doing at massive scale on billions of web pages, but we could actually do it by hand on this 8-node graph. And here's how we do it. Suppose we wanted to find the equilibrium PageRank values on these 8 nodes. And there's clearly some unknowns here. So let's declare the PageRank in the equilibrium at node A to be X. X is an unknown that we're going to try to solve for. Now, in terms of X, we can actually make a lot of progress figuring out what the equilibrium is. Because if these PageRank values are going to regenerate themselves after each step, it says that the PageRank at B and at D should be X over 3, because that's what they're going to get from A, which has X. Similarly, if B and D each had X over 3 and A had X, then C will get the X over 3 from node A, and it will get X over 6 from each of B and D. And so, in other words, it will, in equilibrium, it better have 2x over 3 if it's going to regenerate its own value. And we can keep going, right? So B has x over 3. So what should E have if after one application of this update rule, it gets the same value back? Well, it should have x over 6, because that's what it's going to get from node B. And similarly, C is going to divide its 2x over 3 in half. It's going to hand it to each of G and H. So they'd better have x over 3 each if they're going to regenerate themselves. And finally, let's check, what does that mean A should have? It better mean that A should have x in equilibrium, or this whole thing isn't going to work. Well, let's see. So it's going to get x over 6 from E and F, and it's going to get x over 3 from G and from H. And so when we add those up, x over 3 plus x over 3 plus x over 6, we end up with x. So it checks out, right? A2 is in equilibrium. And so these values, these 8 values expressed in terms of x, actually form an equilibrium of PageRank. And so that will be our set of equilibrium PageRank values. Except for one small thing, which is we haven't worked out what x is. And here we're going to use the one extra piece of information we have, which is that the total amount of PageRank in the whole system is 1, which means all these numbers I've drawn here expressed in terms of x add up to 1. Right, let's write them all down. So there's an x plus x over 3, another x over 3, plus 2x over 3, there's 2x over 6s, and 2 more x over 3s. And when you add all those up, you get 10x over 3. That should be 1, so now we just solve a little equation. 10x over 3 equals 1, or in other words, x equals 3/10. Or to make the arithmetic a little easier, all the way down to the bottom, 6/20, like I drew in the beginning. Okay, and that's how we could actually find these magic numbers that I drew for you, the equilibrium PageRank values. We write down some unknowns. The rest of the values are implied by the equilibrium, and we then solve for what the unknown value is. Okay, so this is a very tidy situation. It's a set of equilibrium PageRank values. They're consistent, right? They regenerate themselves every time we apply the update rules, and so this really seems to be how the endorsement is flowing in the graph. And in a sense, this would be the end of the story, except there turns out to be one thing wrong with all of this. The problem isn't mathematical. It's not a mathematical problem, because everything works mathematically just as advertised. The problem is that sometimes these numbers don't actually make any sense as scores for the pages. They don't intuitively reflect how we think the endorsement ought to be flowing. And so in order to understand this, our first task is going to be to look more deeply at the network structure, to diagnose what this problem is, when it occurs, how to fix it, and in that way we're actually going to arrive at the definition of PageRank that's actually used in practice.